Hello, CS 341 students. I'm Professor Anna Lubu, and I'm doing the lectures for the second half of the course. So a reminder of what we've done so far. The course so far has been about algorithmic paradigms. In particular, we've looked at reductions, which will come up again in a later part of the course. Looked at divide and conquer algorithms, greedy algorithms, and dynamic programming. And we are going to revisit all of these in the context now of graph algorithms. So there's a section of the course coming up now on graph algorithms. I like this section very much because graph algorithms are one of the things that I study the most. Okay, so what is a graph, first of all? I'm assuming you've seen graphs in previous courses, Math 239, basically. So a graph has vertices, and we are going to use elements 1 through n as the vertices of the graph. I'll say more about that in a moment. The edges of a graph are pairs of vertices, and we often draw graphs as pictures. So here this graph has these 5 vertices, and which edges are there? There is, for example, the edge 1, 2. So I have the pair 1, 2. And because this is an undirected graph, I could list it as 2, 1, just the same as 1, 2. So you can see that, for example, the pair 1, 4, that is not an edge of this graph. Now, a directed graph, by contrast, the edges are ordered pairs. So here I have the edge from 1 to 2, but I do not have an edge that goes from 2 to 1. It's not in this graph. Between vertices 1 and 3, I have the edges going in both directions. So we indicate that this way. Now, one thing we're going to assume throughout this section of the course is that we never have loops. A loop would be an edge that goes from a vertex to itself. We're not going to allow them. And secondly, we are not going to allow multiple edges. There are some contexts in which those are useful, but we're not going to need them. So I am not allowed to have, for example, 2 edges going between the edge 2, 3 over here. Now, as to make these things a little bit more concrete, let's think a bit about how many edges a graph can have. So we are thinking of there being n vertices, and we want to ask how many edges can there be. At this point, I think I will turn off my video because I'm going to be looking down at the iPad as I'm writing for you. So first of all, in an undirected graph, the number of edges, which we call m, can be 0, or it can be as many as, think about it a minute, n choose 2, because that's the number of unordered pairs. So we're looking at n times n minus 1 over 2. That is the maximum number of edges. On the other hand, for a directed graph, we get more possibilities. So again, the number of edges is between 0, but now the upper bound becomes n times n minus 1. Right? So twice as many, because I have this option here of having edges in both directions. Okay, so what do we get out of this? That the number of edges is always big O of n squared. We can't have more than that. But there are some graphs where we can have that many. So I'm going to say that it can be, in the maximum case or the worst case, it can behave like n squared. Now, one reason to pay attention to this is that a graph with few edges, in particular a graph with a linear order n number of edges, is called sparse. And sometimes we can have algorithms that work much more efficiently on sparse graphs than they do on very dense graphs. Okay, so next I have a slide that is somewhat full, but I thought it's helpful to have all these things in one place. So some basic notions about graphs. We say that 2 vertices u and v are adjacent, or they're neighbors, if we have an edge between them. So for example, vertex 1 and vertex 3 here are adjacent, they're neighbors, but vertex 1 and vertex 4 are not neighbors. When we have U as a vertex and E as an edge, we say U is incident to E if it's one of the endpoints of the edge. So vertex 5 is incident to this edge. Vertex 5 is not incident to this edge 2, 3. Now for an undirected graph, we talk about the degree of a vertex, which is the number of edges incident to it. So for example, vertex 5 here has degree 1, 2, 3. It has degree 3. Vertex 4 has degree 2. It is possible to have a vertex of degree 0. That means it's an isolated vertex and there are no edges coming into it. Now, for a directed graph, we talk about the in degree and the out degree, because we distinguish whether the edge is pointing into the vertex or pointing away from the vertex. So in this little example, this vertex here has 2 edges coming in. So I say the in degree is 2. And on the other hand, it has 3 edges going out. So the out degree is 3. Okay, next up, what is a path? I'm thinking you've seen this before when you've looked at some graph theory, but a path is a sequence of vertices such that each pair, like V1 to V2, has an edge between them. So I have, let me draw a little picture. I have an edge from V1 to V2. And in a directed graph, I would want that edge to be directed from V1 to V2. And I continue, and eventually I have an edge that leads to the last vertex of the path, which I was calling V sub k here. The length of a path is always counted by the number of edges. So not the number of vertices, but the number of edges. So the number of edges in a path will be 1 less than the number of vertices in the path. And we say that a path is simple if it does not repeat vertices. So if I took a path here going from 5 to 1 to 2 to 3, oh, that's a bad example. Let me start over. If I went from 5 to 3, 1, 2, 3, 4, that is a path from 5 to 4, but it is not a simple path. A simple path would be just doing this. And one thing to observe is that if I do have a path, then I can always take away the repeated parts and get a simple path. Next up, what is a cycle? A cycle is a path that starts and ends at the same vertex. So for example, going from 5, this would be a cycle. I end up back at the same vertex 5. And then we say that a cycle is simple if it doesn't repeat vertices, except that I start and end at the same vertex, right? The length of a cycle is the number of edges. That's completely consistent with the way we count the length of a path. Now, one thing I'll caution you about is that some textbooks and some web pages, if you look at them, they use the word path to mean a simple path. So when in doubt, just check which meaning is intended, and we'll try to be clear on any assignments. Okay, 3 more things here. A tree is a connected, undirected graph without cycles. So for example, this is a tree on 3 vertices. This, however, is not a tree because I have a cycle in it, right? And if I think of this as a whole graph here, that is not a tree because it's not connected. Or if I think of these 2, I don't have any cycles, but again, that is not a tree because it's not connected. Now, I should have said first, perhaps, what does connected mean? An undirected graph is connected if every 2 vertices in the graph are joined by a path. So I do not have a path from here to here. So this whole graph here is not a connected graph. And the number of connected components is just the number of pieces. So in this case, 3, the number of connected components. Good. So graphs have been studied for a very long time by mathematicians, starting with Euler in 1735, who formulated this for the purpose of the Königsberg bridge problem. So the town of Königsberg had a river going through it with a couple of islands. Here's one and here's one. They're drawn here as these green blobs. And it had some bridges. And one of the games for young couples was to go for a walk and try to cross every bridge exactly once. So they might have started here and crossed to the island, crossed to the North Shore, crossed here, crossed here, crossed here. Oh, whoops, there are two possible bridges, but if you take this one, you would have to repeat this bridge in order to catch that one. So that was a failed attempt. And when Euler abstracted this by drawing the graph corresponding to this, so here's the North Shore, the South Shore, the one island, the larger island, then it's easy to see that there is no way to cross every bridge. The bridges are now these black edges of the graph. There's no way to make a tour, an Eulerian tour it's called, that goes over all these bridges exactly once. And the reason is that all of these vertices have odd degree. So here, 1, 2, 3, 4, degree 5, here's degree 3, degree 3, degree 3. And if I start somewhere and go through a vertex, and maybe I come back and go through it a second time, I always visit the vertex an even number of times. So there is no way I can visit all the edges exactly once when there are more than 2 vertices of odd degree. Now, I suspect that the young couples who were doing this game of trying to cross all the bridges didn't actually care too much if it's possible or not. This was their evening entertainment back in the 1700s. Anyway, there are many, many applications of graph theory, and I'd suggest looking at the Wikipedia page for a taste of some of them. I'm going to show you a little bit, some pictures of various graphs. So one is the kind of graphs you get from road networks, as shown over here. So subway maps, road maps, the vertices can be thought of as either the intersections where 2 roads meet, or perhaps on a larger scale, the vertices would be the cities, and roads are, the edges are the roads that connect the cities. Here is an example of a graph that might indicate clusters in some data. So every vertex here is representing some data point, and the edges are representing relationships amongst them. Here I have an example of a graph that arises from Wi-Fi networks. If you think that every Wi-Fi node is a point in the plane and it can reach for a certain distance, and then for 2 of these Wi-Fi nodes, I say they can communicate if the 2 distances overlap. And then we get graphs as this example shows with the black edges. And finally, over here, I have a picture of some of the names that people have attached to various graphs. One famous graph you might know particularly well is this one, which is K5, the complete graph on 5 vertices. And another one you might have encountered, both of these when you were studying planar graphs. This one is here called the utility graph, but you might know it as K33. The complete graph with 3 vertices, the complete bipartite graph with 3 vertices on one side and 3 on the other. It's called the utility graph because of this puzzle where you say, I have 3 houses and 3 utilities. I would like to connect every house to every utility and make that as a planar graph. And if you've seen a bit of Kuratowski's theorem, for example, you know that that's not possible. Okay, I have some more pictures here of graphs arising in various ways. And if you might look at this picture for a little bit of time and try to think where each of these graphs is arising. Like, do you recognize what this graph is showing? Have you ever seen a graph like this? Have you seen the Stanford bunny in this form? So here I have the same slide, but captioned. So this first graph is the graph is what's called the Sierpinski triangle, but it arises from the Towers of Hanoi puzzle. Each vertex here, each node of this graph is showing one configuration for the Towers of Hanoi, and an edge indicates one move that you're allowed to make, where you move one disk onto another peg in such a way that the peg underneath, the disk underneath is larger than the one you've just moved on. And so it's interesting that the Towers of Hanoi, which you have probably seen before, you may not have seen that it leads to such an interesting graph when you think about all the possible configurations of the game and how you get from one configuration to another. This graph is a dependency graph of some Apache software. What a mess of edges, isn't it? Yeah. This graph, I'm thinking here of the graph as consisting of these little nodes that you can just see as these dots, and the edges are making these triangles on the surface of the Stanford bunny. So this is a very nice graph. It's a planar graph, and there are very nice properties of it. For example, the number of edges, it will be a sparse graph. The number of edges is linear in the number of vertices that you've used. And I wonder if people recognize this. This was Darwin's drawing of an evolutionary tree. And this is caffeine, which we can think of as a graph again, with lots of six-sided cycles, hexagons. Now, we're going to be studying graph algorithms. So an important thing then is how we're going to store graphs, what kind of data structures we're going to use. Now, we're going to focus on really sort of core graph problems, abstract graph problems. It's great to know all these applications, but we're not programming the applications. We're thinking of the graph as an abstract structure. In particular, we are always going to think of the vertices as being numbered from 1 to n. When I talk about them, I might call them V1 through Vn, just because sometimes we have too many numbers floating around, and it's good to indicate V to indicate a vertex. Which vertex? Vertex number 2, okay? And we might sometimes just use letters. So I'll say for each vertex V in the graph, do something else. Look at vertex A in this graph, but really we are storing them as the numbers from 1 to n. Now, in practical applications, graphs have labels for the vertices and for the edges. So we do need, for such applications, we need a mapping from the labels to the vertex numbers. And hashing and maps, those are great ways to do that. And we're not going to be concerned with that in this section of the course. I have to here, well, this was the caffeine where we see it's important that the nodes are labeled here. And here is a graph that comes up from a database application. I guess the red nodes are indicating a person because a person likes this purple node. The purple node has as author this person. So I presume this is a book or something else that a person can author. And some of these directed edges are indicating friends. I would think friends should go in both directions. Okay. So also in applications, there's another complication, which is that we often have graphs that are changing over time. So we want to add and delete vertices and edges. These are called dynamic graphs. And we're not going to be concerned with that. That's a more advanced topic, is to store a graph subject to changes in the graph. So we're going to be thinking of static graphs, and the vertices are numbered from 1 to n. Okay, so with that understanding or that simplification, how are we going to store our graphs? There are two basic ways called the adjacency matrix and the adjacency list. Now, the matrix is maybe the easiest thing to understand. So if there are n vertices, I will make an n by n matrix. The columns are indexed by the vertices and the rows are indexed by the vertices. And an entry inside here is 1 if there's an edge between vertex I and vertex j, and 0 otherwise. So I have a little example down at the bottom, and let's look right away at how we would represent this graph with an adjacency matrix. So I have vertices 1, 2, 3, 4, and I record the same vertices down the rows. I'm going to fill in this 4 by 4 matrix. And one thing you should note right away is that because we don't have loops, that is, we don't have an edge from a vertex to itself, I'm going to have zeros down the main diagonal. How about 1 and 2? Are they joined by an edge? Yes, they are joined by an edge here. So I put a 1 in the matrix there. And it's an undirected graph, so the matrix is symmetric. The edge 2, 1 and the edge 1, 2 are the same thing. Is there an edge from 1 to 3? Yes, there is. So that's this entry. Is there an edge from 1 to 4? There is not. Okay. And finally, 2 to 3, there is an edge. 2 to 4, there is not. And the very last one, is there an edge from 3 to 4? Yes, there is. Okay, so that's the adjacency matrix. Now, adjacency lists are a little bit different. For each vertex, I'm going to store a linked list of its neighbors, or in the case of a directed graph, of its forward neighbors. Okay. So coming down to this example again, I would have an array, 1, 2, 3, 4. And for each place in the array, I would start a linked list of all the neighbors. So vertex 1 over here has neighbors 2 and 3. So I would list them here. 2 and 3. Vertex 2 has neighbors 1 and 3. Might be listed in the other order. I'm not going to make an assumption about that. Vertex 3 has neighbors 1, 2, and 4. So maybe they appear 1, 4, 2. And vertex 4 only has the single neighbor 3. Now, an advantage of the adjacency list structure is that the size behaves like theta n plus m. So I have a number of vertices down here, and every edge, for example, the edge 1, 2, is appearing in two places in this list, right? From 1 to 2 and from 2 to 1. So I'm recording every edge twice, essentially. And as I mentioned before, the number of edges in a graph can be anything between 0 and n squared. So to capture this variability, we often measure graph algorithms in terms of both of these parameters, n and m. And so it's nice to say, okay, the space is order n plus m, and that's the smallest that it can be. I have n vertices, I have m edges, that I need at least that amount of space. Okay, by contrast, the adjacency matrix, it takes n squared space. So this matrix, even if it has a huge number of zeros in it, that is, m is very small, I am still explicitly storing all of the zeros for the non-edges and using space n squared. Okay, so I have here a slide where I'm inviting you as an exercise to work out for a directed graph, like this one in this example, what does the adjacency matrix look like, and what do the adjacency lists look like? And there are more examples in your textbook. And another good source for this basic graph stuff is the online book of Jeff Erickson's. There's a link to that from the course webpage. Now, I've been talking theta n plus m without yet saying what model of computing are we using for graph algorithms? How are we measuring space? How are we measuring time? We're using a word REM. That's our basic model of computing, and it's totally appropriate to use for graphs. Now, if you remember, we discussed early on in the course, Professor Brown discussed these two models, the bit model and the word RAM model. The difference is the bit model counts how many bits we've used to count space or input size, and it counts the number of bit operations for time. This model is appropriate for problems, for example, where I have 1 or 2 numbers as input. And so some examples would be multiplying 2 numbers. which was an example. You saw a divide and conquer algorithm to do that. Another example would be if I want to test if a number is prime. So here the input is a single number. And to say how good is that primality testing algorithm, I would want to say, how does it behave in terms of the number of bits in the original algorithm? So on the other hand, the word RAM model sort of abstracts away from this bit model. When we talk about sorting taking n log n time, we're not thinking in terms of a bit model. We are thinking that I can compare two numbers in a unit cost. And for that, it's the word RAM model that we use. We are counting words for space and counting the size of the input in terms of the number of words we're given, and counting word operations as each one taking unit time. So how do I count time? I just count how many word operations were there. Now, to keep this realistic, we have to limit how many bits there are in each word. Otherwise, I can make one word that has the entire code of the program in it, for example, or the entire input, and that's cheating. That's not allowed. So we're going to limit the number of bits per word. And the way that's done is if the input consists of capital N words, we allow the number of bits in each word to be log of capital N. And if you recall, the rationale for doing this is that if I wish to store n words, I have to be able to address them. I have to count from 1 to capital N. I need those different addresses for each one. So I need log n bits just to fit an address into one word. So that is a reason why we should not say that W is a constant. And on the other hand, we don't want W to be even larger than that, because then we get the danger of sort of cheating and cramming too much into a single word. So examples here are sorting. The input is n numbers. We often write little n, but I'll be consistent here and write capital N for the number of things we're given. And we say sorting takes n log n. If the numbers fit into order log n bits. Okay, so in particular, it would be inappropriate to use the bit model here. I would end up with a log squared factor because I'd have to take into account how big the numbers are. And we don't think about sorting that way. Okay, and on the other hand, this word RAM model is not so appropriate if we're thinking about multiplying two numbers. Here, capital N is equal to 2, and my restriction here would be saying that, oh, I'm only allowed to store a constant number of bits in each word. It's not the appropriate model. Okay, so, but coming back to graphs, a graph has n vertices. They are the numbers from 1 to n. Each one needs log n bits. We know how many edges we have, and we are going to use the word RAM model. So we're going to say that the input size is n plus m words to capture the order n plus m words to capture the input graph. And we will measure running time in terms of n and m. Later on in the course, we're going to think of having weights on the edges of a graph. For example, in a road network, the weight would be the distance you travel. And there again, we will use the word RAM model. In other words, we will assume that the weights are not huge numbers, that they fit into log of n bits, order log of n bits, and we will assume that arithmetic on those weights takes unit time. Just one word operation to do that. Okay, so coming to basic graph operations then, the really basic things we would like to be able to do with graphs are, given a vertex, to list all of its neighbors. Now, if I have an adjacency matrix, I have to look through the row corresponding to V, and it'll be a list of ones and zeros. And from that, I can extract all the neighbors. But it's going to take me theta n time. On the other hand, with the adjacency list, I just look down V's list, and it's going to take me basically the degree of V. But I'm going to say 1 plus the degree of V, just in case the degree is 0. It still takes me constant time to do that, not 0 time. Listing all the edges with the adjacency matrix is going to take me n squared time, whereas with adjacency lists, I can do it in time proportional to the number of edges plus the number of vertices. So in both of these first two cases, the adjacency lists are preferable. It takes less time here than it does here. Now, the one exception is this test. If we're given two vertices u and v, and we want to know, is that an edge? With the adjacency matrix, I just look at that place in the matrix and see if it's a 1 or a 0. On the other hand, if I have adjacency lists, I can't do anything better than check the whole list for u or for v. I could check whichever one is shorter, but still, it's going to take me time, like 1 plus the degree of one of these vertices. Okay, so on the next slide, I'm going to compare these a tiny bit more. Let's also look at space, though, as I commented already. This takes n squared space. Here, I have what's called linear space, so theta n plus m. So for algorithms in this course, maybe let me move to the next slide here. Our algorithms in this course, we're going to use only these two operations. We're going to try to avoid this one. In fact, there is a way with adjacency lists to improve this with some sophisticated hashing techniques that are sort of beyond the scope of this course or of CS240, where you saw hashing. So for algorithms in this course, we're going to use adjacency lists. Occasionally, we might use the matrix, but then we'll explicitly say so. And I guess I've said this already, but when we have a graph algorithm and it runs in order n plus m time, we say that's a linear time algorithm. It's linear in the input size, which is n plus m in our word RAM model. Okay, so that was the first part of this lecture. In general, in my lectures, I'm going to have these purple colored slides occasionally as sort of pause points, where if you're tired of watching a video all in one sitting, you can pause at this point. Each time I'm going to summarize. So far we saw definitions of graphs and paths and trees and so on. We saw how to store graphs. What you should be able to do from this first part of the lecture is know how do we store graphs, how to work with adjacency lists, what order n plus m means, and how big m can be. And next, we're going to talk about exploring graphs. Okay, so now we're turning to the topic of exploring a graph. This will be review because I know you have seen breadth first and depth first search before, perhaps in the context of trees only, and here we're doing it for graphs. So the idea of exploring a graph is that we want to visit all the nodes, or perhaps all the nodes reachable from some source node, some starting node or vertex. And furthermore, we are going to, in the process of doing that exploration, we're going to be able to find shortest paths, find connected components, and do other good things that I'll tell you about. Now, the first method of exploring we're going to look at is breadth first search. And in the next lecture, we'll look at depth first search. So what is breadth first search? It's a cautious way of searching a graph where we check all the vertices one edge away from the start node, then I go to the vertices that are 2 edges away, and so on. So if I start with vertex 1 here, I would then explore its neighbors, these ones, and then I would start exploring maybe from vertex 8, is there anything else I can get to? From vertex 6, can I get to something else? And so on. So to fill in something more of this example, I would start with vertex 1. I'm making what's called a breadth first search tree, and I'm going to put all of its neighbors in the next level. So it has a neighbor 2, 3, 6, and 8. Those are the neighbors. And now I will start with vertex 2 and look at its neighbors. They are 4 and 5. I guess when I'm at vertex 2, I also say, oh, I have this edge from vertex 2 to vertex 1. So I have to notice that that was already there, right? So I'm only exploring the new vertices that I have not already seen. When I explore from vertex 3, what am I going to find? Vertex 1, which I've already seen. Vertex 6, which I have already reached it as a neighbor of vertex 1. Vertex 4 and vertex 5. So let me draw these in here. I would say, oh, I can get to 6, which is already there. I can get to 4, and I can get to 5. But those are already in my tree. So there's nothing new to reach from vertex 3. Next, I will look from vertex 6 and discover that there's one new thing I can see, vertex 7. And I explore from vertex 8, and I find that there's nothing new. And then I would continue and explore from vertex 4, but I've already seen all its neighbors. Vertex 5, there I see neighbors, let me see, 2, 3, and 7. So 2 and 3 I've already seen, 7, I have it already waiting for me. And finally, from vertex 7, there are just those 2 edges. So this would be the complete breadth first search of this graph. I call these nodes level 1 nodes, and these ones are level 2. This one we can call level 0. Okay, and just to put this in another way or another context, the order in which the vertices are discovered. First I find 2, and first I find vertex 1, and then I find its neighbors. 2, 3, 6, 8. So these are the neighbors of 1. It's neighbors. And then I'm next exploring vertex 2, and I would then add on its neighbors here. So 4 and 5. So 2's neighbors. I'm going to abbreviate neighbors, it's too long. And vertex 7 appears as, I explore 2, I explore 3, I explore 6, and that's where I discovered vertex 7. So vertex 6's neighbors. Neighbors. Okay, so this is an example of the breadth first search of this little graph. Now, here is the pseudocode for doing the breadth first search. We're going to use a queue. That's the appropriate structure for the way I was doing that exploration of vertices, right? We use a queue to store the vertices that we've discovered, but we haven't yet explored. And the vertices are initially marked as undiscovered, and we change them to discover when we first encounter them. So how does the explore subroutine work when I'm exploring from a particular vertex? I look at each neighbor of the vertex V, and if that vertex U is as yet undiscovered, then I say, now I'm discovering it, and I add it to my queue to be explored later. The entire breadth first search from a particular start vertex, if you recall in the previous picture, vertex 1 was our start vertex, right? We would initialize by marking every vertex undiscovered, and I would put my initial vertex into the queue, mark it as being discovered, and then while the queue is not empty, I pop a vertex from it and explore it. So that would, when I explore 1, I add vertices 2, 3, 6, and 8 to the queue, and then I'm done with vertex 1. The next vertex on the queue is vertex 2. So that's what I explore next. So this queue behavior is precisely what we wanted here. Now, it's useful to store something more when we go through this. This explore and breadth first search, I'm not doing very much except marking vertices through time. So we do want to store the parent pointers, and we also want to store the levels, the way I indicated levels over here, right? So let's see how we would do this. The time when I discover vertex U, this is the time to declare what is its parent. The parent of U is assigned V, and the level of U, I also know this at this point in time, and that will be the level I was at for V plus 1, right? Because all these edges that I'm discovering, they are going from one level to the next level. They're the tree edges. The one more thing I need to add here is that when I initialize with V0, I should say the parent of V0 is empty. It's the root of my tree. And the level of V0, this is to get us started here, is 0. Okay, so this is the complete code for our breadth first search. And here it's written in just with, I've just typed what I hand wrote before. Here's what's new on this slide is how much time does this breadth first search take? It takes order n plus m. And the reason is that I explore each vertex once, exactly once, so long as I can reach that vertex from V0. And if you look at the code for explore, it's just a constant amount of work going on here. Well, constant, no, that's not quite fair. I have a loop that says for each neighbor U of V, so I have to take into account how many neighbors does that vertex have. So the time is linear plus the sum of the degrees of all the vertices. And here I've written that that is going to be order n plus m. And the reason is that the sum of the degrees is twice the number of edges because every edge is counted twice, right? The edge from U to V appears once when I look at the degree of U, and it appears once when I look at the degree of V. So every edge is counted twice in this sum. This is something that, you know, it seems obvious when I explain it. You should probably think it through a little bit more. There will come times when you need this, and then you should come back and say, oh, that red box was something that I should remember and use. Okay, so we're going to talk about some properties of breadth first search, 3 properties in particular. There's 2 of them on this slide already, and a third one will come later. So the first property is that the parent pointers of my breadth first search create a directed tree. And the idea here is that, you know, I have created some part of the tree so far, and when I discover vertex V, I point up to its parent. So when we discover V, vertex V, we set its parent. So if you think of this as directing the edge from the vertex to the parent, every vertex except the root, which has the empty parent, right? Every vertex has exactly one parent, and that's exactly the notion of a directed tree in the computer science sense. Yeah. The second property here says that if UV is an edge, then the level of U and the level of V differ by 0 or 1. In other words, this is saying I would never have some kind of edge that goes from level 0 to level 2, or from level 2 to level 5, or something like that. All of the edges both the tree edges and these extra non-tree edges, they just go between one level and itself, like this, or between one level and the next level. So let's look at the proof of this. So the first thing to note is that the way that Q works in the breadth first search is that we explore all the vertices on one level before we start on the next level. So we explore all vertices on level I before we explore anything on level I plus 1. So let me put it explicitly, before starting level I plus 1. I plus 1. It's a little bit messy, sorry. So if you think of what does the picture look like in general, there is some part of the tree that I have explored. Here I'm drawing it as though I'm partway through this level at the bottom here. Now, there are some vertices that I've discovered. They're the explored ones, but plus also everything that's waiting in the queue. And that will consist of the remainder of this level plus something in the next level. So it'll look something like this. In particular, I have vertices here that I have already explored, and I have discovered their neighbors in the next level, right? The vertex that I am currently exploring is this one, vertex V. It's the start of my queue, the first vertex in my queue that I've just popped off the queue, and I'm about to explore all of its neighbors. Now, V had some parent up here. Maybe this has some more things. There's some more things. So these guys here and here are things that have been discovered. So all of the blue stuff is discovered. But these ones here have been discovered but not explored. They are waiting in the queue. Okay, so now when I come along, let me now come back to what we're trying to prove. If UV is an edge, I want to look at the levels of the two vertices. So let us suppose between U and V, suppose V is explored first before U. Remember, we are in an undirected graph here. So suppose V is explored before U. And I want to look in this picture here, the situation when I explore from vertex V. So I'm going to look at the various neighbors of vertex U. I might find that there is a neighbor here that is in my large pool of undiscovered vertices. If you look back at the pseudocode, that was the first line. I look at a neighbor U of V, and if it's undiscovered, then I set its parent and I put it into the next level, all right? So if, let me back up one step and say one more thing before this. So we check all edges going from V to U. And I want to look at all these possibilities. So now, if U is undiscovered, as shown in the picture, then I set the level, right, at that point. If you look back at the pseudocode, I set the level of U to be the level of V plus 1. Okay, so that certainly works as far as proving what we wanted to prove. The level of U and V are going to differ by 1 in that situation. On the other hand, so else U is a discovered vertex, but it's not yet explored, right? Because we made this assumption that U was explored before, sorry, V was explored before U. So else U is discovered, but not explored. And we showed where those possible vertices lie here. It could be a vertex like this one. And it could be a vertex like this one. So these are the possible places where that vertex U can be. So thus, it's in the same level as V, or the level of V plus 1. Okay, because those are the only vertices here and here. Those are the only vertices that are in the queue. They've already been discovered, but I have not yet explored them. Okay, so that's this proof. Now, I promised you 3 properties about breadth first search. And so here is the third property. It says that a vertex is connected to my starting vertex V0 if and only if breadth first search from starting at V0 reaches vertex V. And there's a stronger phrasing of that, which is that the level of a vertex V is the length of a shortest path from V0 to V. So for example, vertex 7 here, if we looked back at that graph, you would see that the shortest path from vertex 1 to vertex 7 is of length 2. It has 2 edges. In particular, we're saying there's no path of length 1 in this little example. That's all it's saying here. Okay, so we're going to prove this property. Let me again emphasize that this is a really important thing. It means that breadth first search is finding shortest paths from V0 to everything else. So later in the course, we are going to look at more complex situations where we want shortest paths. Maybe we have weights on the edges. Maybe we have a directed graph. But the most basic version of shortest paths is this one, and breadth first search does it. We have an undirected graph, and we have no weights on the edges. Every edge just counts as 1 in the length of a path. Breadth first search is the secret. Okay, so let's look at this lemma. It says that a vertex is on level I if and only if the shortest path from our start vertex to V has length I. This is another way of saying this, right? We're going to prove this by induction on I, and first case being the base case, being when I is equal to 0. So vertex V is on level 0. Well, that means it has to be this one, right? Our start vertex. If and only if the shortest path from V0 to V0 has length 0. That's certainly true, okay? So that's an easy case. Shortest path V0 to V0 has length 0. It's sort of a degenerate case of a path. It has no edges at all. The start vertex and the end vertex are the same. It's a legitimate path, and that path has length 0. Okay, so now we are going to consider the case of larger I and assume that this statement we wish to prove is true for all values of j smaller than I. So we're going to look at the 2 sides of this. In the first direction, we will suppose that vertex V is on level I. Okay, so maybe we are looking, for example, at this vertex 7. And what do I know about it being on level I? I know that its parent is on the level before that, right? So that's going to be my secret to doing induction. So parent of V is on level I minus 1. And then we can say, okay, by induction, I know that the shortest path from V0 to the parent of V has length I minus 1. And in particular, I'm going to make a weaker version of that and just say there exists a path V0 to parent of V of length I minus 1. Induction tells me something stronger, which is that that's the shortest possible length, but I'm not even going to use that. Okay, so out of this, I can then say there exists a path from V0 in terms of my picture here, I've said, oh, there's a path from the start vertex to the parent of vertex 7 of length 1. Now I'm going to add to vertex 7 and get one more in the length. V0 to V of length I. And is this what I wanted to prove? I wanted to show that the shortest path, V0 to V, has length I, but let's consider that. If there is a shorter path, so let me put here, is it shortest? That's the last thing we have to consider. If there is a shorter path, then what I'm going to do is use the induction statement going the opposite direction. Say, oh, if there's a path from V0 to V that's shorter than length I, then I get to apply induction and say that vertex V is on a level before I. So again, by induction, V is on a level less than I, which is not what we assumed, right? We assumed that vertex V is on level I. All right. So that completes the one direction. And the other direction, we are starting by saying, all right, the shortest path, V0 to V, has length I. And I am going to, again, do this trick of looking at the second last vertex of the path. So let U be the second last vertex of the path. Okay, so then we have the shortest path from V0 to U has length I minus 1. Certainly there is a path of that length, and if there were a shorter one, well, then I would get to V in length less than I, so that's not possible. Okay, so the shortest path has this length, and therefore by induction, let me see. U is on level I minus 1. And this will imply by our property 2 here. So this is important. This is where we're using property 2, which says that if I have a vertex U on a certain level, and there's an edge from U to V, then vertex V has to be on level I minus 1 or I. The levels differ by at most 1. So V is on a level less than or equal to I. And again, this is not the precise thing we wanted to show. We wanted to show that V is on level I. And here what we've got so far is that V is on a level less than or equal to I. But we do the same thing as before. If V is on a level less than I, let me see. Then by induction, there's a shorter path from V0 to V. Okay, we assumed that the shortest path had length I, so we shouldn't be able to find a shorter one. So this is an induction proof. I know you're all masters of induction proofs. I guess the one thing I'll say about this is that it has this weird final thing about using induction at the very end to get the stronger thing we need. And this was a reason why I did induction for the whole if and only if, rather than you might imagine a different structure that says, I will first prove the forward direction by induction, and then I will prove the backwards direction by induction. Here we did the if and only if statement by induction. So that's one interesting thing to note. Okay, I don't think I'll write it down though. All right, so we've now seen 3 properties of breadth first search. And now what I'd like to do is show you how to use those properties for getting some nice information out of breadth first search. So again, this is for undirected graphs. Please note that. So the first application is that I can find all the connected components of a graph. And if you remember, we once had a picture that said, you know, if I have a graph that has various disconnected pieces, I might wish to find that here there are 3 connected components of this graph. How can we do this with breadth first search? I'm leaving it as an exercise, but I'll at least tell you the idea and leave it to you to enhance the pseudocode. I would pick some vertex for my start vertex, maybe this one. I would do a breadth first search and I would be discovering all of this, and then I would run out. My breadth first search would stop. And what do I do at this point? I should say, oh, well, I've only discovered these 1, 2, 3, 4, 5 vertices. There are undiscovered vertices still waiting for me. So let me pick an undiscovered vertex, maybe this one, and do a breadth first search from that. Oh, now have I seen the whole graph? No. So I again start at a new vertex and do a breadth first search there. So each time I start from a new starting vertex, I'm finding a new component. And so I invite you to fix up the pseudocode, make a bigger loop around the breadth first search from V0 to find all the connected components. Okay, the second application is the one we just talked about on the previous slide, which is to find the shortest path from some start vertex to any other vertex V. I could do that here, for example. If I started here, I would find, oh, all these 3 vertices are distance 1. The shortest path is length 1 from my start vertex. However, all of these guys, the distance is infinity from my start vertex. Yeah. The third application is to test if a graph has a cycle. And for that, it's worth looking here at this picture and noticing these dashed edges that were not part of the tree. What do you see about those dashed edges? If I add them into the tree, they're the ones that make the cycles, right? So that is a hint for how to do this exercise and discover out of a breadth first search whether or not the graph has cycles. The fourth one is one I would like to spend a little bit more time on, and that is testing if a graph is bipartite. So let's look at that. Now, first of all, what does it mean for a graph to be bipartite? I said it briefly at the start of the lecture, but here's the formal definition. A graph is bipartite if I can partition the vertex set V into 2 sets. And if you remember what partitioning means, it means that V1 union V2 would be the whole set, and V1 intersect V2 is the empty set. That's what a partition is, yeah? So a graph is bipartite if we can partition the vertices into the 2 sets such that every edge goes in between the 2 sets. So I have my V1, I have V2, all the edges go in between here. Doesn't mean that every pair here has an edge. This pair doesn't have an edge. It just means that any edge that I look at goes across the split here. I never have an edge that's just inside V1 or an edge that's just inside V2. Now, the first thing I'd like you to note, you've probably seen this in Math 239, is that if a graph is bipartite, then it cannot have an odd length cycle. So think about that. I start here, I take 1 edge. Oh, I'm on the other side. 2 edges, I'm back on the first side. 3 edges, I'm over here. Whenever I've done an odd number of edges, I can't be back at my starting node, right? Because I'm in the other set. If I had an edge here now, I have an even number of edges and I'm back where I started. So that's the argument why a bipartite graph does not have an odd length cycle. So here's our algorithm to test if a graph is bipartite. It's really simple. I run the breadth first search. I take my set V1 to be all the vertices in the odd levels. So if we think about our level structure, which I guess I was drawing in blue, then I'm saying that I would put into V1 all the odd levels, and I would put into V2 all of the even levels. Maybe let me draw one more even level just so, yeah. So this is my partition that I'm declaring. And then I'm just going to test if that partition works. So for every edge, I'm going to check if U and V are both in the same set, either V1 or V2, I'm going to return no. This is not a bipartite graph. And otherwise, I return yes. Okay. So the runtime is just the breadth first search here, and then linear time to do this. And here I'm checking through all the edges. So order M here. The runtime is order N plus M. And let's look at correctness. If the algorithm returns yes, it means I found a partition that shows that it's bipartite. So that part's good. And the other half is that I must prove that if the algorithm returns no here, that the graph is not bipartite. In other words, if this partitioning here doesn't work, the claim is that there's no partitioning that is going to work. And we prove that in a beautiful way by showing that if the algorithm returns no, then the graph has an odd cycle. And we know that if it has an odd cycle, it cannot be bipartite. So let's have a look at that. So the claim here is that if there is an edge that lies entirely inside V1, V1 is the odd levels, or entirely inside V2, which is the even levels, then the graph is not bipartite. So suppose there is an edge, there's an edge UV that lies entirely inside one of these parts. So I equals 1 or I equals 2. But the both vertices lie in the same vertex set. Okay, then we're going to again use that property 2 of the breadth first search, which said that if we have an edge, then the level of the two vertices involved differ by 0 or 1. Okay, but is it possible that the level of U and the level of V could differ by 1? That would mean one has to be in an even level and one in an odd level. So they can't differ by 1. I guess I don't want to explicitly say which one is in which set because I never did identify that, but we would have one in V1 and one in V2. Okay, that's not possible. So we know that U and V are in the same level. And let's suppose that that is level K. All right. So let me draw a picture of things. I think I've been using blue for my level set. So here's my level K. And I have two vertices U and V that are both in this set. And I have some edge. I'll make it a dashed edge because it's not one of the edges of the tree, right? There's a dashed edge going between them. And what I would like to do now is find an odd length cycle that's in this graph somewhere. Now, the secret is that U and V have to be connected some other way. I'm going to look up my parent pointers, up the tree from U and up the tree from V, And at some point, those are going to meet. And I call that the least common ancestor. But in other words, I just take the path from U up to the root of the breadth-first search tree, the path from V up to the root of the breadth-first search tree, and the place where those two paths first meet. Okay, and this is in the parent tree, or the tree of parent pointers, parent edges. And now we have a cycle, don't we? Because this edge together with this path makes a cycle. So we get a cycle. I'll call it C, and let me draw it in red just so that we can see it. And so this is the cycle C. And now I want to look at the length of this cycle. Well, it's the length of the path from U to Z. And remember, we have to go up levels and levels, right? So the length of C, I claim, is, if I call this length T, then this length here has to be the same length. Let me write it in a little bit better in this picture. So the length is exactly, the length in the breadth-first search tree is exactly the number of edges. So the length is 2T plus 1. The 1 is arising from this very last edge between U and V, right? And both of these have the same length because I'm going from level K in both cases to whatever level vertex Z is in. So to make that really truly explicit, if I said, suppose Z in level L, then T is equal to level K minus level L plus 1, right? No plus 1. Oh, I always have trouble with my off by 1 errors. Okay, so this is an odd cycle, odd length cycle, right? I'm only looking at this number and saying it's of the form even number plus 1, so it's an odd number. It's an odd length cycle, and therefore the graph G is not bipartite. Okay, so that's a beautiful little proof. And the one thing I'd like to say more about it is that this proof was by way of an algorithm. The proof said either either a graph is bipartite or it has an odd cycle, and not both things can happen. It's another way of saying this. G is bipartite if and only if it has no odd cycles. So either a graph is bipartite or it has an odd cycle, and not both. And the proof is via an algorithm that finds one or the other of the or statements, either a bipartition or an odd cycle. So one thing I like very much about this is that it mixes a beautiful mathematical if and only if statement with a beautiful algorithm that sort of effects the if and only if. So it's computer science and mathematics shaking hands with each other. Okay, so that's the end of this lecture. In summary then, we did graphs, definitions, data structures, and then the second part of the lecture was on breadth-first search. And what you should know is the basic stuff, plus how to use breadth-first search, what it's good for, what the properties of it is, when you can use it. Remember, this is for an undirected graph. And next, we're going to look at depth-first search, which we will use both for undirected and for directed graphs. Okay, and that's it for this lecture. Thank you.